Hello and welcome. These are the solutions to quiz 44. So the first question here talks about the Goodyear blimp. Gives a volume of helium, temperature, and pressure. How much helium does the blimp contain in kilograms? So for this problem here, we're just relating PV is equal to nRT for a gas. We can do this one of two ways. We can either just set PV equal to m over molar mass, because that's moles times RT, or we can just solve for moles of helium that would be present and then convert that over to grams. Let's actually just use the ideal gas law equation like this, solve for N as PV over RT. And the only thing we have to pay attention to is units. So our pressure, 770 torr. Now I'm going to convert to ATM just because of my constants I'm going to use for R. This is the only units other than joules per mole Kelvin that were given for R on exams, and so it's just easier to convert torr over to ATM. I think we have to memorize this conversion, but we do it a bunch. 760 torr per ATM. So our ATM cancels. Obviously, we're going to multiply by the volume. 5.1 times 10 to the 6 kilograms. Oops. 5.1 times 10 to the 6 kilograms. And then we'll divide by the temperature, but of course in Kelvin. So 24 plus 273 is 297 Kelvin. And we work this out. Here we get our moles. Just doing the math here, it comes 5.1 e to the 6, divide by 0.08206, and then divide by 297, and I get 212,000 moles of helium. Everything cancels here except for 1 over moles. This was liters, I wrote kilograms, but that was really the liters. And so then we just do 1 mole of helium, 4.003 grams in the periodic table, 1,000 grams per kilogram. So we'll write this in kilograms. So multiply by 4.003, and divide by 1,000. So I get 850 kilograms. So 8.5 times 10 to the 2. For the next question, it's been a question I've kind of always wanted to delete just because it's kind of tricky. And it's, really the idea here is so the density of air is the mass per unit volume. So if we're thinking about density, it's pressure times molar mass divided by RT. Well, our density would just be additive, like we could calculate the density of O2 from the pressure of O2 times the molar mass of O2 divided by RT. We can write the density of N2 the same way. It's the pressure times the molar mass, but of N2, and it's the partial pressure of N2. So this would be the partial pressure of O2. And then divide by RT, and then the same thing for argon. So it would be pressure times of partial pressure of argon times the molar mass of argon, divided by RT. You could simplify this perhaps and do some averaging out here, calculate an average molar mass and take your total pressure for your total density. That's one way to do it, but I think if you just take your total density as the sum, the density just from O2, the density from N2, plus the density from argon, and the only tricky part here is our partial pressure of O2 will be our total pressure times the mole fraction of O2. And the mole fraction of O2 is just like the 0.21. And so the total pressure at STP is 1 ATM. So the partial pressure of O2 is therefore just 0.21 ATM. Okay, so the density of O2, I'm just going to do this without showing the math. So it would be the 0.21 ATM, but then times the molar mass of oxygen, grams per mole, is 32 grams per mole. And then we'll divide that by 0.08206, and then divide that by 273 because that's STP. So that gives me 0.300 for the density of oxygen. In fact, let me write this out for one of these just up here. So the density of O2 would just be equal to the partial pressure of O2, 0.21 atm, so just the mole fraction, 0.21 times an atmosphere, then times the molar mass of oxygen, 32.00 grams per mole, because we're using the grams per mole of O2, and then the gas constant, 0.08206 liter atm mole Kelvin, and then STP is an infinite number of ATM, so it's like exactly 1 ATM, 273.15 Kelvin, or 0 degrees C. It's these temperatures and pressures exactly. And so that's where I got the 0.300. Now how do the units go here? ATM cancels, mole cancels, Kelvin cancels. We got grams per liter. Let me just do this for N2, so it's 0.78 times molar mass of nitrogen, 28, and then divide by 0.08206, and then divide by 273.15, 0.974 grams per liter. And the density of argon is going to be pretty low because its partial pressure is really low, 0.009. So we got a partial pressure 0.009 atm. Molar mass of argon is about 40.05. And then times, or divide by the gas constant. And then divide by 273.15. And so it's contributing just 0.016. So we just want to add these up here. So 0.016 plus 0.974 plus 0.300, about 1.29, rounding to 2 sig figs, 1.3 grams per liter. A gas sample with a volume given 750 milliliters. So 750 milliliters exerts a pressure of 756 millimeters of mercury at 30 degrees C. What pressure will this sample exert when it's compressed to 250 milliliters at minus 25 degrees C? Okay, so we have, we know PV over NT is equal to our gas constant. And the sample here isn't changing the quantity, so we're changing the pressure, so the pressure is changing. That's actually what we're going to be looking for. Our volume can change, but the moles can't change. Moles are constant, but then the temperature is changing too. So we can do one of two things. We can move maybe the moles over to here, since they're constant. The only thing that's changing is P1 V1 over T1. And then we know that, PV over T would be equal to N times R. Let me rewrite this here so we write in the same notation like nRT. So I just want to write this as nR as well. So our P2 V2 T2 should still be equal to N times R, because N's not changing, R is not changing, they're constant. And so PV is equal to nRT. If we're changing the pressure, volume, and temperature, they're both equal to nR, so therefore they have to be equal to each other. So that's how we come up with this simple relationship here, that P1 V1 over T1 is equal to P2 V2 over T2. And the only caveat here is we just have to plug temperatures in Kelvin. We can't plug a negative temperature in. Or even if both temperatures are positive, we have to convert over to Kelvin. So we have to be in the absolute temperature scale is the only real caveat. So we're looking for the, what pressure in ATM will the sample exert. So P2 is our question mark. So P2 is going to be P1 V1 T2 divide by T1 V2. Okay, and then we're just plugging in. So our P1 with 756 millimeters of mercury. I'm going to leave that at 756. Let's actually write this out over here. So 756 millimeters, 750 milliliters. Again, I'm going to leave that in milliliters. And then T2 is here. So minus 25 is 273 minus 25. So that's 248 Kelvin. And then I'm going to divide this by T1, which is 30 degrees C. 30 plus 273, 303 Kelvin. And then times V2, the compressed volume is 250 milliliters. So the milliliters I can leave in milliliters. I don't want to cross the 250 out. I want to cross out the milliliters. The milliliters I can leave in the same unit. Degree C I can't. Degree C I have to convert to Kelvin. Millimeters of mercury, I can leave this as is and then just convert over to ATM since it asks for the pressure in ATM. So let's do 756 times 750 times 248 divided by 303 divided by 250 gives me 1856, but this is still millimeters of mercury. So P2 would be 1856 millimeters of mercury, and then 760 millimeters of mercury per ATM. So I just need to divide by 760. I get 2.44 ATM. So I get answer B. Consider a cylinder fitted with a movable piston that can expand against the atmosphere. The initial pressure and volume and absolute temperature of the system with the pressure. So cylinder movable piston can expand against the atmosphere. The initial pressure, volume, and absolute temperature inside the cylinder are P1, V1, T1. What's the new temperature of the system when the pressure is increased to 3 times the initial pressure? So P2 is equal to 3 times P1. And the original, and the volume is decreased to 1/2 of the original volume. And so what's the temperature? So it's T2. So we go to P1 V1 over T1 equal to P2 V2 over T2. Our T2 will be equal to P2 V2 T1 divided by P1 V1. Okay, and so all we're doing here is plugging in that P2 is 3 times P1. And then we got 1/2 times V1 times T1 divided by P1 V1. So P1 cancels, V1 cancels. And so this should be 3/2 times T1. The answer here should be 3/2, 1.5 times T1. There we go. Okay, tricky problem, but this is just, you're tripling the pressure. Having the volume has to therefore lead to an increase in the temperature. All right, on to page 2 of the activity here. So we have, the airbag inflation reaction. So if an airbag has a volume of 48 liters to be filled with nitrogen at a pressure of 1.5 atmospheres at a temperature of 27 degrees C, how many grams of the solid is required in order to decompose into that nitrogen gas, according to the reaction above? So what we want to do here is use PV equal to nRT to calculate the moles of the gas, the moles of the N2. So the moles of N2 that are going to be in the airbag that we need to fill it will be PV over RT. So we need this to go to 1.15 ATM. We need this to go to 48 liters. We need to divide by the gas constant. We need to multiply by the temperature that this is going to happen at. So slightly warm temperature, 27 plus 273 is 300 Kelvin. Kelvin cancels, ATM cancels, liter cancels, 1 over moles gives us our moles. Let's work this out. 1.15 times 48, divide by the gas constant, divide by 300 Kelvin. It's 2.24 moles. And so then how many grams of sodium N3 do we need? This comes from a stoichiometry problem. We know we need 2.24 moles of N2. Well, for every 3 moles of N2 that we need to produce, we need to start with 2 moles of NaN3. 1 mole of NaN3 would be about 22.99 or about 23, plus 14 times 3. So it's 65.0 grams per mole. So 2.24 times 2 divided by 3 times 65.0. That's going to be about 97 grams. If we flip this back into a sig fig problem, we only had 2 sig figs here. So we should only be carrying 2 significant figures in our final answer. Okay, so we have a gram sample of SFX where we don't know what X is. We just know we either have 1, 2, 3, 4, 6 sulfurs, has a volume of 270 mils, the given pressure at the given temperature. What is X? Well, this is one here where using this equation here might be the best go, because we're given the pressure of the gas, the volume of the gas, the mass of the gas. We don't know the molar mass. But we can solve for it because we know the temperature. So we know every variable here except molar mass. So our molar mass will be equal to MRT divided by PV. Okay, so we take a gram times a gas constant, this is 0, 0.08206. Write your units out in this chapter. This is a good tip so we don't make a mistake. 75 plus 273 is 348 Kelvin. And we're going to divide this by 745 millimeters of mercury, 760 millimeters of mercury per ATM. So we can cancel ATM here. And then the volume, we go into liters, 0.270 liters. So our liters cancels, our Kelvin cancels, everything except grams per mole cancel. So we have grams per mole. We go 1.00 times 0.8206 times 348 divided by 745. In fact, let's do this way. 1 times 0.08206 times 348. Then let's divide by, and let's go ahead and use a parentheses. 745 divided by 760 times 0.27, close parentheses. That gives me a molar mass of 107.9. So the question is, which of these has a molar mass of 107.9? So sulfur is 32.06. Fluorine's about 19. So that's only 51 if there's 1. 32 plus 19 times 2, not enough. 32 plus 19 times 3, not enough. 32 plus 19 times 6, too much. 32 plus 19 times 4, 108. So we're right over here at 4. So this would be SF4, would be consistent with this molar mass. So at this point here, you're just trying to come up with which molar mass is consistent with this molar mass. It'd be SF4. Now you could subtract off the sulfur and divide by the molar mass of fluorine. Might be another trick of finding out that it's 4. So we could take 107.9 minus 32.06 for the sulfur and just divide by 19, and there we get 3.99. So a few ways you can come up with the answer to number 6. Number 7, we have an empty container filled with 40 grams each of helium and argon, 75 degrees C. What is the total pressure inside the container, assuming the gases behave ideally? So our total pressure would just be the sum of argon plus helium. And so, we could simplify, like if we were to write this out and recognize that we're just taking PV is equal to nRT, so this is nRT divided by V, but for the argon, and this is the nRT divided by V for the helium, we might be able to simplify, but I think it's just easy enough to plug in and solve for this problem twice. So we go 40.0 grams of helium divided by 4.003 grams per mole. Let's change this divide sign to multiply by this per 1 mole. 2 grams to moles for N, and then times R. And then times T, 75, is 348. I guess the 75.0 kicks us into 348.15 Kelvin. And then we'll divide by the volume of the container, 3.75 liters. And then we're going to take plus the 40.0 grams of argon. The molar mass of argon, I think it's 39.95. I don't have a periodic table nearby. Let's just go 39.95. It's either that or 40 point something, but I think it's 35.95 grams per mole of argon. And then times the same R, liter ATM, mole Kelvin, 348.15 Kelvin, and then divide by 3.75 liters. So we could have done some rearranging to simplify the math, but I think this is easy enough. So we do 40 divided by 40 divided by 4.003 times the gas constant times 348.15 and divide by 3.75. So for just the helium, that's pretty high. Let me go recalculate that again. So 40 divided by 4.003 times 0.08206 times 348.15 divided by 3.75. Yeah, so I did miscalculate something the first time. So this, for the partial pressure of helium, I get 76.1 ATM. Got 1 sig fig here, and then the partial pressure of argon would be 40 divided by 39.95 times the gas constant times 348.15 divided by 3.75 gives me 7.62. So we got about a factor of 10 less moles of the argon because of its higher molar mass. So 7.62 ATM. Just add the two together. The total pressure is just the sum of the two. $83.7. There we go. Must have been at least pretty close on the molar mass of argon for this problem here. Okay, so those are the solutions to quiz 44.